What if the thing shaping the entire universe, the thing guiding its future, defining its structure, is something we can't see, something we can't touch, or truly understand? When we talk about the universe, when we talk about what it's made of, it's one of those things that sounds simple, doesn't it? You look up at the night sky and you see stars. You see the faint, misty glow of the Milky Way. If you have a good telescope, you can see other galaxies, spiraling islands of light far, far away. And you might think, well, that's it. That's the universe. Matter, light, and gravity pulling it all together. But the more we look, the more we listen, the more we realize that what we see, it isn't the full picture. In fact, it's not even most of the picture. It's just a tiny fraction. It's like standing on the shore of an ocean, dipping your toe in the water and thinking you understand the entire sea. The truth is, all the stars, all the galaxies, all the planets, all the atoms that make up you and me and this world around us, all of it only accounts for about 5% of everything that exists. The rest, 95%, is something else, something invisible. And the biggest part of that invisible world, the component that truly dominates the cosmos, is something we call dark energy. It's a strange name, isn't it, dark energy? It's not dark in the sense of being black or shadowy, and it's not energy in the way we usually think of it, like electricity or heat or the light from a star. It's just a name, a label we've put on a mystery. It's a way for our minds to hold on to an idea that is almost too vast to grasp. This thing, this presence, it makes up almost 70% of the total energy and matter content of the universe. 70%, the vast unseen majority. We don't see it, we don't feel it. It doesn't seem to interact with us in any way at all, except for one. It controls the fate of everything. We didn't find it by looking for it. We found it by accident. We found it because the universe wasn't behaving the way it was supposed to. For most of the 20th century, we had a simple, elegant idea. After the Big Bang, the initial explosion that started everything, the universe was expanding. But it was also full of stuff. Matter. And matter has gravity. Gravity pulls things together. So the great cosmic question was, is there enough gravity to stop the expansion? We thought there were two possibilities. Either gravity would eventually slow the expansion down and pull everything back together in a distant fiery future we called the Big Crunch. Or if there wasn't enough gravity, the expansion would just slow down and coast forever, getting slower and slower, but never quite stopping. That was the assumption. Gravity was the brakes. The only question was how strong the brakes were. So in the late 1990s, two separate teams of astronomers set out to measure this, to measure the rate at which the universe was slowing down. They did this by looking for some of the most spectacular events in the cosmos exploding stars. Specifically, they looked for something called a Type 1a supernova. These are special. They are what happens when a certain kind of star, a white dwarf, dies in a very particular, very violent way. And the wonderful thing about them for astronomers is that they always explode with almost exactly the same predictable brightness. They are what we call standard candles. Think of it this way. If you see a row of streetlights stretching down a long dark road, you know how bright each one is supposed to be. By looking at how dim a distant streetlight appears, you can tell exactly how far away it is. The dimmer it looks, the farther it must be. These supernovae, they are cosmic streetlights. The astronomers used the most powerful telescopes in the world, including the Hubble Space Telescope, to find these explosions in galaxies billions of light years away. They would measure how dim they appeared, which told them how far away they were. Then they would measure their redshift, how much their light had been stretched by the expansion of the universe. This told them how fast that part of the universe was moving away from us. They were mapping the history of cosmic expansion, looking deep into the past. They expected to see that the most distant supernovae, the ones from the early universe, were moving away faster than the expansion rate today. That would be the proof that gravity was putting on the brakes, that the universe was slowing down. But that is not what they found. They found the opposite. The distant supernovae, the streetlights in the deep past, were dimmer than they should have been. They were fainter, which meant they were farther away than all the models predicted. It took a long time for the teams to believe their own data. They checked everything. They rechecked everything. But the conclusion was inescapable. The only way those supernovae could be so far away is if the expansion of the universe hadn't been slowing down at all. For the last several billion years, it has been speeding up. Imagine throwing a ball up into the air. You expect gravity to slow it down to make it stop and to pull it back to your hand. Now imagine throwing that ball and watching it, instead of slowing down, suddenly shoot upwards faster and faster, accelerating away from you into the sky. That is what we saw. That's the universe we live in. It was a discovery that shocked the entire world of science. It changed everything, because if the universe is accelerating, something must be pushing it. If gravity is the foot on the brake, then something else, something enormous, has its foot on the gas. And that something is what we call dark energy. It's not a force that comes from a place. It seems to be a property of space itself, an intrinsic energy woven into the very fabric of the void. Where there is space, there is this pressure, a gentle, constant, repulsive force, an anti-gravity. On small scales like inside our solar system or even inside our galaxy, gravity wins. It's much stronger. It holds the planets in orbit. It holds our galaxy together. But in the vast empty oceans of space between the galaxies, there is just so much space, and all that space adds up. All that gentle pushing over millions and billions of light years becomes the most dominant force in the cosmos. It's a force that doesn't get weaker as things move apart. In fact, as space expands, more space is created, and with more space comes more of this dark energy, more push. So the more the universe expands, the faster it expands. We are living in a runaway universe, and we are only just beginning to wake up to the fact that we are afloat on an invisible ocean, an ocean that is quietly, relentlessly, and powerfully pushing everything apart. Now, it's important to say that this dark energy isn't the only mysterious dark thing in the universe, and that can be confusing. You've probably heard of dark matter as well, and while they share a name, they are, in a way, complete opposites. They are the two great invisible forces in a cosmic tug-of-war. Dark matter. We've known about that for much longer. We see its effects everywhere. We see it in the way galaxies spin. They spin so fast that by all rights they should fly apart. The stars on the outer edges are moving too quickly. The gravity from the visible matter, the stars and gas we can see, isn't nearly strong enough to hold them in orbit. There must be something else there. Something invisible, massive and heavy. A vast, unseen halo of stuff that surrounds the galaxy, holding it together with its immense gravity. That is dark matter. It makes up about 25% of the universe. It is the hidden scaffolding. It is the gravitational anchor that pulls things together, that allows galaxies to form and clusters to hold their shape. It clumps, it gathers, it pulls. Dark energy is the opposite. It is not matter. It doesn't clump, it doesn't gather. It seems to be perfectly smooth, perfectly uniform, spread evenly across all of space, and it doesn't pull. It pushes, so you have this beautiful, strange balance. Dark matter is the gravity trying to build structures, trying to pull all the galaxies together. And dark energy is the invisible ocean, the swelling of space itself trying to push them all apart. Right now, in the era of the universe we live in, dark energy is winning. And the strangest part of this story, the most poetic twist, is that the best idea we have to explain it comes from a ghost. The ghost of an idea from Albert Einstein over 100 years ago, an idea he himself called his biggest blunder. To understand this, we have to go back to the early 20th century. Einstein has just completed his masterpiece, The General Theory of Relativity. It's a new theory of gravity. It says that gravity isn't a force pulling things. It says that massive objects like stars and planets literally bend and curve the fabric of space and time around them, and other objects in turn just follow those curves. That's what an orbit is. It was revolutionary. And when Einstein looked at his own equations, they told him something profound. They told him that the universe must be dynamic. It couldn't just sit still. The combined gravity of all the matter in it would inevitably cause it to collapse in on itself, or it must be expanding. But this was in the 1910s. The common sense of the time, the absolute belief among all astronomers and physicists, was that the universe was static, it was eternal, it was unchanging. It had always been here, and it always would be perfectly balanced, perfectly still. Einstein, for all his genius, was a man of his time. He looked at his equations, and he looked at the static universe everyone believed in, and he thought, my equations must be wrong. So he tinkered. He added a new term, a little piece of math, a fudge factor really, that he inserted into his beautiful equations. He called it the cosmological constant, in Greek the letter lambda. It was a tiny hypothetical energy, an anti-gravity, that he built into the fabric of space itself, a force that would perfectly precisely balance the pull of gravity on large scales. It was just enough of a push to stop the universe from collapsing, holding it in that perfect static eternal state. It was a mathematical trick to make his theory match the universe he thought he lived in. And then, just a few years later in the 1920s, an astronomer named Edwin Hubble changed everything. Using a massive new telescope, Hubble looked out at the distant fuzzy patches in the sky, the nebulae, and proved they were in fact other galaxies, entire other universes of stars just like our own. And then he measured them, and he found that almost all of them were moving away from us. And the farther away they were, the faster they were moving. The universe wasn't static, it wasn't eternal and changing, it was expanding. The very thing Einstein's original equations had predicted, the universe was dynamic. When Einstein heard of Hubble's discovery, he realized his mistake. He had bowed to common sense instead of trusting his own mathematics. He had mutilated, as he put it, his theory. He immediately removed the cosmological constant, famously declaring it was the biggest blunder of his life. And for decades, that's what it was. A historical footnote, a mistake. The one time Einstein's intuition had failed him. The constant lambda was put away in a drawer and forgotten, until the 1990s, until those teams of astronomers looked at those distant dying stars and found that the expansion wasn't just happening, it was accelerating. Suddenly, cosmologists were faced with a problem. Something was pushing, something was acting like an anti-gravity. They needed a force to drive this acceleration, and someone remembered the ghost. They went back to that old discarded idea. They pulled Einstein's blunder out of the drawer and looked at it again, and they realized it was perfect. It was a small, constant, repulsive energy built into the fabric of space. It's exactly what the data was calling for. It describes a universe that for the first few billion years is dominated by the matter and gravity. But as space expands and matter thins out this constant, this push, which doesn't thin out, slowly begins to take over. Until just as we observed it becomes the dominant force and starts to accelerate the expansion. Einstein's biggest blunder might have been his most profound and prescient discovery. He had predicted dark energy in 1917 without to 80 years before we ever knew it existed. So today, the cosmological constant lambda is our leading model for dark energy. It fits the observations beautifully. It's the simplest explanation. But it leaves us with an even deeper question. If dark energy is this constant, if it is this energy, what is it? What is the physical source of this energy? And the best answer we have is that it is the energy of nothing. It's the energy of empty space itself, the energy of the vacuum. This idea comes from our other great theory of reality, quantum mechanics. In the quantum world, the world of the very, very small empty is not a peaceful concept. A perfect vacuum, a patch of space with all matter and radiation removed, is not empty. It is fizzing. It's a roiling, chaotic soup of energy. There is a fundamental rule in the quantum world, the uncertainty principle that says you can never have perfect stillness. You can never have exactly zero energy. There is always a minimum and underlying jitter. We call it the 0-point energy. Think of the ocean again. From a satellite, it looks perfectly smooth, perfectly still. But if you're on a small boat, you see it's a turmoil of waves and foam and ripples. The vacuum of space is like that. It is full of quantum fields, and these fields are constantly fluctuating, constantly jittering. This quantum foam creates pairs of virtual particles that pop into existence and then annihilate each other in fractions of a second. A constant underlying hum of energy present in every single cubic centimetre of space, everywhere, all the time. And according to Einstein's relativity, all energy, all of it, has a gravitational effect. It curves space. So scientists had this breathtaking thought. What if dark energy is the 0-point energy? What if this quantum jitter, this energy of the vacuum, is the physical source of Einstein's cosmological constant? It was the most beautiful idea. It would have united the two pillars of physics relativity, the science of the very large and quantum mechanics, the science of the very small in a single profound concept. So they did the math. Physicists sat down and tried to calculate how much energy should there be in the vacuum according to quantum theory. They summed up the jitters from all the known quantum fields, the electron field, the photon field, all of them. And they got a number. It was the most wrong number in the history of science. The calculation, the prediction from our most successful theory of reality, said that the energy of the vacuum should be enormous, catastrophically large. The number we observe for dark energy, the gentle, subtle push we see from the supernovae, is tiny. It's a whisper. The number our theory predicts is a scream. The difference between the two is a 1 followed by 120 zeros. 10 to the power of 120. It is a number so large it's meaningless. It's larger than every atom in the known universe. If the vacuum energy was really that strong as quantum theory predicts, the universe would have been torn to shreds in the first 10 to the minus 40-something seconds of its existence. We would not be here. Stars would not exist. Space itself would have instantly exploded. We call this the vacuum catastrophe, and it is perhaps the biggest, deepest, most terrifying mystery in all of physics. We have an observation, a gentle acceleration. We have a beautiful theory to explain it, Einstein's cosmological constant. And we have a perfect candidate for what that constant is, the energy of the quantum vacuum. And yet, when we try to connect them, the numbers are so wildly, comically, disastrously wrong that it tells us only one thing. We are missing something fundamental. Either our understanding of quantum energy is deeply flawed, or our understanding of gravity is. Or perhaps there is some vast, beautiful, unknown symmetry of nature that cancels out almost all of that enormous quantum energy, all 120 zeros of it, all except for one tiny leftover fraction. A fraction that is just enough to be the ghost in the machine, just enough to be the invisible ocean that is slowly, quietly pushing our universe apart. That enormous, baffling disagreement, that gap of 10 to the power of 120 between our best theory and our best observation, it's so profound that it forces us to wonder. It makes us ask, what if our simplest assumption is wrong? What if dark energy isn't constant? Einstein's blunder, the cosmological constant, it's a single unchanging number. It assumes the energy density of empty space is the same today as it was a billion years ago, and as it will be a billion years from now. It's simple, it's elegant, and it fits the data pretty well. But what if dark energy is dynamic? What if it's not a static feature of space, but rather a field that fills space? This idea is called quintessence. It's a beautiful word, isn't it? It comes from the ancient Greeks, who believed in a fifth element, beyond earth, air, fire, and water, a perfect celestial substance. In modern physics, quintessence is the name for a hypothetical invisible field that stretches across the entire cosmos. Unlike a constant, a field can change, it can evolve. We can imagine it like a ball, very, very slowly rolling down a very, very long, shallow hill. Its energy isn't fixed, it changes as it rolls. This would mean the push of dark energy wasn't always the same strength. Maybe in the early universe it was weaker. Maybe in the future it will grow stronger. Or maybe it will fade away entirely. This possibility that the acceleration isn't constant, that it's evolving, makes it incredibly important to map the universe's history in as much detail as we can. The supernovae, those exploding stars, were the first clue, but they are just one tool. We need to check the story with other methods to see if they all agree, and we have found them. One of the most powerful is something called baryon acoustic oscillations. It sounds complicated, but the idea behind it is wonderfully simple. It's an echo of a sound from the beginning of time. In the very early universe, for the first 30,000 years after the Big Bang, the cosmos was not transparent as it is today. It was a hot, dense, opaque fog, a plasma of particles and light all coupled together. In this hot soup pressure, waves could travel. They were quite literally sound waves. Just as a pebble dropped in a pond creates ripples that move outwards, any small dense clump of matter in this early fog would create a pressure wave, a ripple of sound expanding outwards into the plasma. Then suddenly the universe cooled enough for atoms to form. The fog cleared, the light was set free. This is the first light we now see as the cosmic microwave background. And at that exact moment, all those ripples froze. The sound stopped. The pressure waves stalled. They left a stain on the cosmos. They left a preferred distance, the exact distance the sound wave had travelled before it froze. This distance is about 500 million light years across. This frozen ripple meant that matter was just a little bit more likely to clump at its centre, and also a little bit more likely to clump along that outer ring 500 million light years away. So today, billions of years later, if we look out and map the positions of millions of galaxies, we can still see this pattern. We see a subtle tendency for galaxies to be separated by the one specific standard distance. This gives us a standard ruler. We know exactly how big that ripple was in the baby universe. By measuring how big it appears to us today at different distances, and thus at different times in the past, we can tell exactly how much space has stretched between then and now. It's like finding rulers of a known size scattered all through cosmic history. It's an independent way to map the expansion. And then there is gravitational lensing. This is pure Einstein. His theory tells us that mass bends space, and if space is bent, light follows the bend. When we look at a very, very distant galaxy, The light from that galaxy has to travel for billions of years to reach our telescopes. On its way, it passes through the universe. It passes by other closer galaxies. It passes through the vast invisible halos of dark matter. The gravity from this intervening stuff acts like a lens. Not a perfect clean lens, but a warped, uneven, cosmic piece of glass. It bends and distorts the light from the distant galaxy. By looking at the images of millions of distant galaxies and measuring how their shapes are subtly warped, how they are stretched and smeared and aligned, we can build a map. We can map the invisible. We can create a picture of all the unseen dark matter that the light travelled past. But it also does something else. The amount of bending, the amount of distortion doesn't just depend on the mass of the lens. It also depends on the distances. The distance to the lens and the distance to the background galaxy. And those distances are determined by the expansion of the universe. If the universe is accelerating, it changes those distances. It changes the geometry, and that changes the amount of lensing we see. So we have these three incredible independent tools: the standard candles of the supernova, the standard rulers of the frozen sound waves, and the map of geometry from gravitational lensing. And here is the beautiful and terrifying part. They all tell the same story. They all confirm in different ways that the supernovae were right. The universe is indeed accelerating. But they also tell us when it started. By mapping the expansion at different times, we can see the whole story. We can see the great cosmic tug of war. For the first half of cosmic history, for roughly the first 7 billion years, the universe was a smaller, denser place. All the matter, both the 5% we see and the 25% that is dark, was closer together. And in that denser environment, the pull of gravity was stronger than the gentle, constant push of dark energy. Gravity was winning the tug of war. So for the first 7 billion years, the expansion of the universe was slowing down. Just as scientists had expected all along, the cosmic brakes were on. But as the universe continued to expand, all that matter spread out. It became more dilute, and as it spread out, its collective gravitational pull got weaker and weaker and weaker. Meanwhile, the dark energy, so that energy of space itself, didn't dilute. As more space was created, more of this energy simply was. Its gentle push remained constant, but as the universe grew, the total push became greater. And then, about 7 billion years ago, a turning point was reached. The weakening pull of gravity finally became equal to the persistent growing push of dark energy, and then it was overcome. The cosmic tug of war was won by the push. The brakes came off and the foot hit the accelerator. The expansion of the universe stopped slowing down and began to speed up. We are living in the era of dark energy. We are living in the aftermath of that great shift in a universe that is now dominated by this invisible repulsive force. You would think, with all these amazing tools, all this data pointing to the same story, that the picture would be complete, settled. But in science, when you get better tools, you don't just confirm old ideas, you find new problems. And right now we are facing the biggest one in modern cosmology. It's a crack in our most fundamental understanding. We call it the Hubble tension. It's a simple disagreement about a simple question. How fast exactly is the universe expanding right now? We have two main ways to answer this. First, we can look at the early universe. We can look at that first light, the cosmic microwave background. This baby picture of the cosmos is so detailed it's like a blueprint. It tells us the exact ingredients of the early universe, how much dark matter, how much regular matter, how much dark energy. We can take this blueprint, feed it into our computers and run a simulation. We can use Einstein's relativity to model the entire 13.8 billion year history of the universe. And this model predicts, it calculates, what the expansion rate must be today. It gives us a number. Second, we can go out and measure the expansion rate directly. We can look at the late universe, the universe around us. We can use our standard candles via the supernovae. We can use our standard rulers, the frozen sound waves. We can look at nearby galaxies and measure right now how fast they are flying away from us. This gives us another number. Here is the tension. The numbers do not match. The number from the late universe, the direct measurement, tells us that the universe is expanding about 9% faster than the early universe blueprint predicts it should be. This is not a small error. These are the two most precise measurements in all of cosmology. The scientists have checked their math. They have rechecked their data. They have accounted for every possible error they can think of. And the disagreement, the tension, remains. What does it mean? It means something is wrong. Something is missing from our story. Is our blueprint from the early universe flawed? Is our measurement of the late universe wrong? Or is the model that connects them, the one that describes those 13.8 billion years of history, incomplete? Maybe dark energy isn't a simple constant. Maybe it's that quintessence. Maybe it changed in a strange way. Maybe there was a burst of early dark energy we don't know about. Or maybe the problem isn't dark energy at all. Maybe it's a new unknown particle, a dark radiation. Or maybe the problem is with Einstein's ghost. Maybe his theory of gravity is, after all, not the final word. We don't know, but that tension, that's the frontier. That's the sound of the universe whispering to us, telling us there is another layer to this mystery. A layer we haven't even begun to peel back. When we step back, when we try to take in all this information from the dying stars, the frozen sound waves, and the warped light of distant galaxies, we can build a kind of inventory, a list of ingredients for the entire cosmos. It's one of the most shocking results in all of modern science. Because when you do the accounting, when you tally up everything that exists, you are left with a picture of the universe that is almost alien. Let's imagine the entire universe is a pie, 100% of everything. We can ask a simple question: what is it made of? Well, we find that the smallest slice, a tiny, almost insignificant sliver, is everything we have ever known. Everything we have ever seen or touched or measured in a lab. The ordinary matter. The technical name for it is baryonic matter, but what it really means is atoms. It's the stuff that makes up you and me, this planet, the air we breathe, the sun that warms us. It is every star you can see in the night sky. It's every galaxy that Hubble has ever photographed, every nebula, every black hole, every grain of dust floating in the void. All of it, every single thing. That slice of the pie is 5%. Just 5%. It's hard to accept, isn't it, that everything we think of as the universe is just the trace ingredient, the foam on the wave. So, what is the rest? Well, the next slice, a much more substantial piece, is that other invisible thing we talked about. The unseen scaffolding, the mysterious heavy stuff that holds our galaxies together with its gravity. That is dark matter. We don't know what it is. We've never found a particle of it, but we know it's there. We see the pull, we see its gravitational fingerprints everywhere we look. That piece of the pie is about 25%. So 5% plus 25%, that's 30%. That leaves the rest, the biggest piece of all, the remainder, 70% of the entire universe. That slice is dark energy. That's the inventory. That's the recipe for the cosmos. A universe that is 70% push, 25% invisible pull, and 5% us. The little bit of leftover material that managed to clump together in the middle of this vast cosmic struggle. 95% of reality is a complete mystery. We don't know what dark matter is. We have no idea what dark energy is. And that isn't just a scientific problem. It's a philosophical shock. It changes profoundly our sense of place in the cosmos. For thousands of years, we've been on a journey of humility, a kind of cosmic dethronement. We used to think the Earth was the center of everything and that the stars and sun revolved around us. And then we learned we were just another planet orbiting the sun, a small one at that. Then we thought, well, at least our sun is special. It's the center. But then we learned our sun is just one very average, very unexceptional star out of 400 billion stars in our own galaxy, the Milky Way. Just a speck of dust in a vast spiral. Then we thought, well, at least our galaxy is the universe. This great island of stars, this must be it. But then we learned in the 1920s that our galaxy is just one out of perhaps 2 trillion other galaxies. An ocean of islands stretching out farther than we can even see. At every step we were pushed further and further from the center. But we still held on to one unspoken comfort. We thought, okay, we may not be at the center of the universe, but at least we are made of the right stuff. We assumed that the universe was made of the same things we are, that it was all atoms, all stars, all gas, that our physics, our chemistry, that was the physics and chemistry of the cosmos. And now we have this, the final dethronement. Not only are we not at the center, we are not even made of the main ingredient. The 5% of the universe that we understand, the matter we are built from, is irrelevant to the large-scale behavior of the cosmos. Our entire world, our entire kind of existence is a side effect. It's a rounding error in the cosmic budget. The fate of the universe, whether it expands forever or rips apart or collapses, is not being decided by the atoms. It's not being decided by the stars or the galaxies. It's being decided by the 95%, by the invisible unknown components that we have only just discovered. We are living in a universe that is not for us. It's not even about us. We are just here, little complex 5% matter creatures who have woken up inside a grand, dark, invisible mechanism that we can't see or touch but that is guiding everything. It's a humbling thought. It's isolating in a way. To realize that our physics is just this local phenomenon, this little pocket of complexity in an ocean of simplicity and darkness. And it leads to another even stranger question, a question of timing. When you look at the cosmic inventory today, you see this split 70% dark energy, 25% dark matter, 5% normal matter. But it wasn't always this way. In the early universe, everything was much denser. All the matter was packed closely together. In that era, the pull of gravity from both dark matter and normal matter was much, much stronger than the gentle push of dark energy. For billions of years, as we said, gravity was winning. Matter was in charge. But as the universe expanded, the matter thinned out and its gravitational pull got weaker. The dark energy, meanwhile, this constant pressure of space, it just stayed. Its influence grew. We live right now in the very special, very specific era where that takeover is happening. We are living at the exact moment in cosmic history when the energy density of matter, all the stuff that pulls, and the energy density of dark energy, all the stuff that pushes are, well, they're roughly the same. In a few billion years, matter will be an afterthought. Its density will have dropped to almost nothing, while dark energy will completely overwhelmingly dominate everything. In the distant past, dark energy was the afterthought. But we are here now. We have woken up at the precise moment of the cosmic handover. This is called the coincidence problem. Why now? Is it just a fluke? Out of the billions of years of cosmic history, is it just a random chance that we evolved minds and telescopes during this one fleeting transitional era? It seems unlikely. If dark energy had been stronger, or if it had taken over much earlier in cosmic history, its push would have overwhelmed gravity from the beginning. That tug of war would have been a blowout. Gravity would never have had a chance. The matter would have been pushed apart before it ever had time to clump. Stars would not have formed. Galaxies would not have formed. Planets would not have formed. We would not exist. If, on the other hand, dark energy was much, much weaker, we might be living in an era where matter is still completely dominant. A universe that might be collapsing or at least slowing down much more. A very different kind of place. But instead, we find ourselves here, in this narrow window, this cosmic afternoon, a universe that is just balanced enough, for just long enough, for gravity to do its slow patient work of building galaxies and stars, and for us to emerge, right at the moment when the sky is beginning to darken, when this new invisible force is taking control and starting to push all those beautiful galaxies away from us. We don't know if this is a coincidence or if it's a clue. Maybe there is some deeper connection. Maybe dark energy and matter are linked in a way we don't understand. Or maybe the answer is simpler and more profound. Maybe we are here because the balance is this way. Perhaps in a vast multiverse of possibilities, we simply find ourselves in the one universe where the laws of physics, the precise balance of the pull and the push, were just right to allow for a 5% sliver of complexity to wake up and wonder. When you think about it, this story of the universe we've been telling, it has a strange kind of symmetry, a beginning and an end that echo each other. We are living now, as we've said, in the era of dark energy, a time when the universe is accelerating, when space itself is swelling, pushing all the galaxies apart. But this isn't the first time this has happened. It's not the first time the cosmos has been in a runaway expansion. To find the other time, we have to go back, not just a few billion years, but all the way back to the very, very beginning. To the first unimaginable fraction of the first second after the Big Bang. In that instant, we believe the universe underwent a period of expansion so violent, so extreme, it's almost impossible to describe. We call it inflation. This wasn't like the gentle expansion we see today. This was exponential. This was space itself stretching faster than the speed of light. An infinitesimally small quantum-sized point blowing up to the size of a galaxy in a fraction of a second. This idea, inflation, it sounds bizarre, like science fiction, but it explains so much. It explains why our universe is so smooth, why it looks the same in all directions. Inflation would have taken any wrinkles, any strange curvatures, and stretched them perfectly flat. And it did something else. It took the tiny microscopic quantum jitters of that first moment, those little fluctuations of energy in the quantum foam we talked about, and it stretched them too. it stretched them into enormous cosmos-spanning ripples. These ripples, these tiny variations in density, would become the seeds of everything. The seeds of galaxies, of stars, of clusters, the cosmic blueprint for all the structure that would ever exist. But what could drive such an unbelievable expansion? The theory is a field. Just like our idea of quintessence for dark energy, we believe inflation was driven by a hypothetical field. We call it the inflaton field. A field that for a fleeting moment was trapped in a very high energy state, a false vacuum, flooding the newborn universe with a powerful repulsive anti-gravity force. And then just as suddenly as it began, this field decayed. It settled into a lower energy state. Its enormous potential energy was released, flooding the universe with the hot, dense soup of particles and radiation that we call the Big Bang. The inflationary push stopped, and gravity took over. So do you see the echo? The story of the cosmos seems to be bookended by a push. It begins with a violent, instantaneous acceleration driven by a field, the inflaton, and it ends, or at least the era we are in is dominated by a slow, gentle, persistent acceleration, driven by what a constant or another field, quintessence. Are they related? That's one of the deepest questions we have. Could dark energy, the thing pushing our universe apart today, be the same field? Could it be a tiny leftover residual echo of the same mechanism that lit the fuse of the cosmos? Or are they two completely separate events, a universe that just happens to have two different pushes, one at the very beginning and one at the very end? We don't know, but it feels poetic, as if the universe has a rhythm, an expansion during a period of coasting and building, and now another expansion, a great cosmic breath, inhaling and now exhaling. But the most important part of the story for us is what happened in between, what happened in that long, quiet middle chapter, after the first push of inflation ended and before the second push of dark energy began. Because that was the era of gravity, that was the time for building. After inflation, the universe was smooth, yes, but not perfectly smooth. It was filled with those tiny stretched out ripples, those seeds, tiny patches of space that were just a little bit denser, one part in 100,000 than the space around them. And the universe was full of matter and dark matter, and all matter has gravity. So for the next several billion years, gravity went to work, patiently, silently, relentlessly. In those slightly denser regions, gravity's pull was just a little bit stronger, so it pulled in more matter, and as it pulled in more matter, its pull grew stronger still, and it pulled in even more. It's a process called gravitational collapse, a runaway effect. The rich get richer. Over hundreds of millions of years, these tiny invisible ripples began to grow. They pulled in vast clouds of hydrogen gas. The gas collapsed. It formed the first stars. Those stars lived and died and seeded space with heavier elements. Those clouds collapsed again, forming the first small infant galaxies. Those galaxies in turn pulled on each other. They merged. They grew. They formed the great spiral galaxies like our own Milky Way. And those galaxies were pulled together into vast clusters. And those clusters were pulled into long, delicate filaments stretching across the void. This is the cosmic web, the beautiful, intricate, lace-like structure of the universe we see today. All of it was sculpted by gravity, pulled from those tiny inflationary seeds. But gravity needs time. It is a very weak, very patient force. It takes billions of years to do this work. And all the while, it was in a race. It was in a race against dark energy. Even in the early universe, even when gravity was the obvious dominant force, that gentle, constant push was always there. It was in the background. It was the swelling of the canvas, even as the artist was trying to paint. Dark energy is the enemy of structure. Its entire nature is to push things apart. It's anti-gravity. Where gravity tries to build, dark energy tries to smooth. Where gravity tries to pull matter in, dark energy stretches the space between the matter, making it harder for gravity's pull to connect. We call this structure formation suppression. The entire shape of our universe, the existence of galaxies, is the result of the balance between these two. And this is where we come back to that idea of the narrow window. What if the balance had been different? What if dark energy had been just a little bit stronger? What if instead of 70% of the universe it was 80% or 90%? What if that push had been just a bit more powerful from the beginning? The race would have been over before it started. Gravity would never have had a chance. Those tiny 1 in 100,000 ripples, the seeds of galaxies, would have been erased, they would have been smoothed out, stretched into nothingness before gravity ever had a chance to grab hold of them. The universe would be a cold, thin, uniform soup, a perfectly smooth, perfectly empty void. There would be no clumps, no cosmic web, no galaxies, no stars, no planets. Alive. The very fact that we are here, the fact that galaxies exist, is proof that dark energy is weak. It's proof that gravity won the race, at least for a while. We live in a Goldilocks universe, one where the push of dark energy was just right, weak enough for just long enough to give gravity a head start. This was the window of opportunity, the era of matter. It was a window that lasted for about 7 billion years. 7 billion years where the pull of all the matter in the cosmos was stronger than the push of all the dark energy. That was the time we had. That was the time gravity had to do its work. To take those tiny seeds and sculpt them into the magnificent, complex and beautiful universe we now inhabit. We are the children of that window. Our existence is the product of a temporary cosmic truce, a fleeting period when the sculptor was allowed to work before the void began to reclaim the canvas. And we have woken up, just as that window is closing. We've woken up in the long cosmic twilight, just in time to see the beautiful structures that gravity built, all those galaxies shining in the night sky. And just in time to see them beginning to accelerate away from us, just in time to realize that the tide has turned, that the push is in control now. We are in a very real sense living in the quiet reflective moment between the echo of one expansion and the slow final oncoming tide of the next. So we find ourselves in this quiet cosmic afternoon. We've woken up just in time to see the beautiful structures gravity has built and to realize that a new invisible tide is beginning to pull them all away. And this forces us to look forward, not just to tomorrow or to the end of our lives, but forward into the deep, deep future. What happens next? Where is this acceleration taking us? The answer, the entire ultimate fate of the cosmos, depends on one thing. It depends on the true nature of that 70%. It depends on what dark energy is and what it will do. Is it Einstein's ghost? A simple, unchanging cosmological constant, a fixed energy of space that will push gently and forever? Or is it something else? Something dynamic like quintessence, a field that is evolving, changing, perhaps growing stronger, or perhaps one day fading away? Because depending on that one unknown answer, the story of the universe, our story, forks into three very different, very final ends. The first path, the one that our current measurements suggest is the most likely, is what happens if dark energy is just what it seems, a simple unchanging constant. In this future, the acceleration just continues, relentlessly forever. The universe keeps expanding and the expansion keeps getting faster. The gaps between the great galaxy clusters grow and grow. Over the next few billion years, we will still see our neighbours. But then as the expansion speeds up, the nearest galaxy clusters will be pushed away from us so fast they will cross a boundary, a cosmic horizon. They will be moving away from us faster than their light can travel towards us. And one by one, they will vanish. Their light stretched beyond visibility will never be able to cross the expanding gulf of space. The night sky in the far, far future will begin to dim. The great tapestry of galaxies will fade light by light as they are pushed beyond the edge of our observable universe. Eventually our own galaxy, the Milky Way, which will by then have merged with our very closest neighbours like Andromeda, will be alone. A single vast island universe. We will be a spiral of stars, floating in an endless, empty, expanding and completely dark void. All other evidence, all other light from all other galaxies will be gone, lost to us forever. But the story doesn't end there. Inside our own isolated galaxy, time continues its slow march. Over trillions and trillions of years, the stars themselves will die. The great clouds of gas that form new stars will be used up. The last generation of small, dim, red dwarf stars will finally sip their last fuel and go out. The galaxy will go dark. All that will be left are the corpses, the cold, dark remnants of stars, black holes, dead neutron stars, and frozen, crystallized black dwarfs. And even they are not forever. Over timescales so vast they defy human imagination, 10 to the power of 100 years, even the black holes themselves will evaporate. They will slowly, painstakingly leak their energy back into the void as faint random particles. And then, that's it. The universe reaches its final state, a state of maximum entropy. We call it the Big Freeze or the Heat Death. It's a universe that is vast, cold, dark, and almost perfectly empty. A thin, cold soup of stray particles drifting forever in an endless accelerating darkness. It's not a violent end, it's not at a fire. It's just a fading, a dimming, a long, slow quiet. Twilight stretching out into an eternal night. That is the first path. But what if dark energy isn't constant? What if that push gets stronger over time? What if that quintessence field we imagined isn't just rolling, but accelerating down its hill? This is a more dramatic idea. We call this kind of energy phantom energy, and it leads to a very different and much more final end. We call it the Big Rip. In this scenario, because the push gets stronger as time goes on, the energy density of space itself increases. The acceleration runs away with itself. At first, just like in the Big Freeze, it pushes distant galaxies away from us. But as the force grows and grows and grows, it will eventually become strong enough to overcome gravity. First, in the distant future, the repulsive force of space within galaxy clusters will become stronger than the gravity holding them together. The clusters will dissolve their member galaxies, flying apart. Then the force will grow stronger still. It will become stronger than the gravity holding our own galaxy together. The Milky Way will be torn apart. Its spiral arms will unravel. Its stars will be flung out one by one into the expanding void. And it does not stop. As the end approaches, the force will become stronger than the gravity holding our solar system together. The planets will be ripped away from the sun. The Earth will be torn from its orbit and sent spinning into the darkness. In the final terrible moments, the push of space will become stronger than the chemical bonds that hold the planet together. The Earth itself will be pulled apart, and in the last tiniest fraction of a second, the dark energy will become stronger than the electromagnetic forces holding atoms together. The very fabric of matter, you and me and the stars, will be ripped apart. A final dissolution. An end where space itself unmakes everything it once held. That is the second path. And then there is a third, an echo of an older idea. What if dark energy is not permanent? What if this quintessence field is temporary? What if it rolls down its hill and then just fades away? What if it decays? If the push of dark energy were to switch off, then gravity, which has always been there, always pulling patiently into the background, would be unopposed. It would be the only force left in charge. And if there is enough matter in the universe, which our measurements say there isn't, but our measurements could be wrong, then the expansion would stop. The cosmic brakes would slam on. And then everything would reverse. This is the big crunch. It's a universe falling back in on itself. A universe in reverse. Galaxies, instead of rushing apart, would begin to rush together. The universe would get smaller and denser and hotter and hotter. It would end exactly as it began, in a single infinitely hot, infinitely dense point, and end not in ice, but in fire. Some have even wondered if that is truly an end. Or is it a big bounce? Could that final fiery collapse trigger another Big Bang? Could it be the seed of a new universe born from the ashes of the old one? A cosmic cycle of birth and death and rebirth, a universe that breathes. A freeze, a rip, a crunch, ice or violence or fire. 3 possible futures, 3 different ends to the story, and the one we are heading for, the one that is written in our stars, is determined entirely by the nature of that 70%. Is it a constant? Is it growing, or is it fading? We are, right now, standing in the twilight looking for the answer. We are staring into the expanding darkness, reading the light from dying stars, trying to understand which of these fates we know is our own. To know that future, to choose between the path of ice or fire or the rip, we have to do more than just wonder. We have to look. We have to become cosmic cartographers. We have to map the past. Because the only way to know what dark energy will do is to find out what it has done. Is it constant? Has it changed? The entire answer is written in the history of the universe's expansion. We just have to learn how to read it. And to do that, we have built cosmic time machines. Our telescopes. They are not just instruments for seeing far away. They are instruments for seeing far back in time. The light they capture has travelled for millions or billions of years to reach us. They are windows into the past. The first and most famous of these is the Hubble Space Telescope. Hubble, it was the pioneer. It was the telescope that, peering into the deep dark void, found those distant dying stars, those standard candles. It was Hubble that gave us the first shocking evidence that the universe was accelerating. It opened the door. It showed us the mystery. But to understand the nature of that mystery, to tell the difference between a simple constant push and a complex changing one, we need more than just a few dozen candles. We need map. We need to survey the whole cosmos. We need millions, billions of data points. And so we are building a new generation of time machines. One of them is a European mission called Euclid. Euclid's job is breathtaking. It is designed to create a three-dimensional map of the universe. It will map the precise locations and distances of billions of galaxies looking back over 10 billion years of cosmic time. How does it do this? It looks for that echo, that frozen sound wave, the baryon acoustic oscillation, that standard ruler that is 500 million light-years long stamped onto the fabric of the cosmos. Euclid will find this pattern, this preferred spacing of galaxies, not just here and now, but everywhere. It will measure the size of that ruler in the distant past, and a little more recently still. By seeing how the apparent size of that perfectly known ruler changes over time, it will create the most precise timeline of cosmic expansion ever made. It will show us in exquisite detail how the push of dark energy has fought against the pull of gravity epoch by epoch. It is quite literally reading the universe's history book. And at the same time we have another, NASA's Nancy Grace Roman Space Telescope. Roman is a hunter. It has a view of the sky that is 100 times wider than Hubble's. Where Hubble sees a grain of sand, Roman sees the entire beach. And it is looking for shapes. It is the ultimate tool for measuring that other cosmic clue, gravitational lensing. As Roman stares at hundreds of millions of distant background galaxies, it will measure their shapes with unbelievable precision. And it will see how those shapes are warped, how they are subtly stretched and twisted by the gravity of all the stuff they have passed on their long journey to us. It will map the lenses. It will create a vast invisible map of all the dark matter, all the unseen scaffolding that fills the space between us and them. This map tells us two things. First, it tells us how structure like the cosmic web has grown over time. We can see gravity pulling things together. But second, it tells us about the geometry of space itself, because the amount of warping, the amount of lensing, also depends on how much space has been stretched by dark energy. Euclid is measuring the timeline. Roman is measuring the geometry. Together these missions, these incredible new eyes, are designed to ask one single driving question: is the push of dark energy a 1? Or is it something else? Is it a perfect unchanging constant? Or is it evolving? They will give us the clearest picture yet of the last 10 billion years. But what if the most important clue isn't in the middle of the story? What if it's hidden in the very first chapter? To see that we have to look beyond the galaxies, beyond the supernovae. We have to look so far back in time that we can see the beginning itself. We have to look for the first light. We call it the cosmic microwave background, the CMB. It is the oldest light in the universe. Think back to that very early time, the first 380,000 years after the Big Bang. The universe was not a dark, empty void. It was a fireball. A hot, dense, brilliant fog. A plasma so hot that light could not travel. It was trapped, scattering endlessly off of particles. Then, after 380,000 years, the universe cooled just enough. The fog cleared, atoms formed, and all of that trapped light was set free. In a single brilliant, silent flash, the entire universe became transparent. That light, that first light, has been traveling ever since. For 13.8 billion years, it has been streaming across the cosmos from every direction unimpeded. It is still here. It is all around us. It fills the sky. It has cooled and stretched with the expansion of the universe, so it's no longer visible light. It is now faint, cold microwaves. When we build satellites to see these microwaves, we are seeing the baby pictures of the universe. We are looking at the wall of that ancient fog. We are seeing the afterglow of creation. And when we look at it, we see that it is almost perfect. It is the same temperature everywhere we look. Almost, but not quite. If you look very, very closely, there are ripples, tiny fluctuations in temperature, 1 part in 100,000. These are the seeds These are the tiny quantum fluctuations from the very first moment of inflation stretched large. These are the seeds that gravity would later sculpt into every galaxy, every star, and every one of us. But what can this ancient light, this picture from 13.8 billion years ago, tell us about the modern mystery of dark energy? It seems like it shouldn't. Back then, dark energy was a tiny, insignificant part of the cosmic budget. It wasn't dominant at all. And yet the clues it gives us are the most powerful of all. They are indirect, but they are profound. The first clue is geometry. The size of those ripples in the baby picture. We can calculate exactly how big they should have been. We know their true physical size. So by looking at how big they appear to us today, we can tell the shape of the universe. If space were curved like a giant sphere, it would act like a magnifying glass, and the ripples would look larger than we expect. If space were curved like a barrel, they would look smaller. What we see is that they are exactly the size they are supposed to be. This tells us, with incredible precision, that the universe is flat. And this is the clue. When we add up all the stuff we can find, all the 5% of normal matter and all the 25% of dark matter, it is not enough. It's not enough gravity, not enough stuff to make the universe flat. The equations of relativity demand a missing component. Something else, something that doesn't clump like matter, something that fills all of space and must make up the remaining 70% of the stuff needed to flatten the cosmos. The cosmic microwave background, its very geometry, is a giant silent cosmic signpost pointing directly at the existence of dark energy. The second clue is the story of growth. The CMB gives us the before picture, the blueprint. It shows us exactly how the seeds were planted. We can then use our other telescopes like Euclid and Roman to look at the after picture, the cosmic web of galaxies that exists today. And we can compare them. We can ask, did those seeds grow at the rate gravity alone would predict? And the answer is no. The models show that for the first 7 billion years, the seeds grew just as expected. Gravity was pulling them together. But then, the growth slowed down. The structures are not as dense, not as clumpy as they should be if gravity were the only force at play. Something stepped in. Something began to suppress the growth. Something began to push back. The CMB gives us the starting line. And by measuring the finish line, we can see the anti-gravity force that kicked in halfway through the race. This ancient fossil light, this echo of the beginning, that it is our anchor. It is our baseline. It tells us in two profound different ways that this invisible ocean, this dark energy must be real. It is all there, written in the oldest light we can see, but in all this talk of constants and fields and strange new energies, there is another possibility, a more radical one, a deeper what if. What if we're asking the wrong question? We've been trying to find out, what is dark energy? What is this new invisible stuff that's pushing the universe apart? We've been searching for a new ingredient. But what if dark energy isn't an ingredient at all? What if it's a sign that our recipe is wrong? The recipe core. The rulebook we use to understand the cosmos on a grand scale is Einstein's general theory of relativity. It's his theory of gravity. And it works perfectly. It predicts the orbits of planets with incredible precision. It predicts the bending of starlight. It predicts the existence of black holes and the ripples of gravitational waves. On the scale of solar systems and stars and galaxies, it is perhaps the most successful theory in human history. But we've just assumed that it also works perfectly over the scale of billions of light years. We've assumed that the law of gravity here in our neighbourhood is the exact same law that governs the vast empty oceans between the galaxies. What if it isn't? What if gravity itself changes? What if over vast cosmic distances gravity just behaves differently? What if it naturally weakens, or what if it even somehow becomes repulsive? In this picture, there is no dark energy, there is no new mysterious stuff, there is no push, there is only gravity, a more complex, more subtle gravity than we ever imagined. What we call dark energy would just be a name for the symptom. It would be the phantom limb of a theory, the part of the equation we had to invent because we were using the wrong rulebook. This idea is called modified gravity. It's a challenging thought. It means questioning our very foundation. It's like discovering that the laws of physics that work in a pond are not the same as the laws that work in the deep ocean. It's not the most popular idea because Einstein's theory is so beautiful and so successful, but it's a serious one, because that's what science does. It must be brave enough to question everything, even its greatest triumphs, when the universe shows us something we don't understand. So that's one path, a universe where our rules are wrong, but let's put that aside for a moment. Let's go back to the other path. Let's assume Einstein was right. Let's assume gravity is what we think it is, and that dark energy is real. We've talked about it being a constant, a simple unchanging push. We've talked about it being quintessence, a gentle rolling changing field. But there is a third possibility, one that comes from pushing that idea of quintessence to its most extreme. To understand it, we just need to know about one simple scientific number. It's a number that cosmologists call to W. The W is simply a measure of how pushy dark energy is. It's the ratio of its pressure to its energy. If dark energy is Einstein's cosmological constant, then W is a perfect unchanging -1. If dark energy is that gentle quintessence field, then W is a number that is more than -1, maybe -0.9 or -0.8. It's a slightly weaker, gentler push. But what if W is less than -1? What if it's -1.1 or -2? This is a line. A boundary, scientists call it the phantom divide. If dark energy has a W that is less than -1, it crosses this line into a whole new and frankly terrifying new territory. This is what we call phantom energy. Phantom energy is different. Its energy density doesn't just stay constant as space expands, it increases. The more space expands, the stronger and angrier its push becomes. This is the runaway universe we spoke of. This is the scenario that leads to the Big Rip. This is a universe where the push doesn't just win the tug of war, it becomes all-powerful. It's a universe that will, in the far, far future, become so violent that it will tear everything apart. Not just galaxies, not just stars, but the atoms themselves. And the frightening thing is, when we make our best measurements, when we look at all the data from the supernovae and the cosmic web and the first light, the number we measure for W is very, very close to -1. It's so close, in fact, that we can't tell which side of the line we are on. The error bars, the margin of uncertainty, they cross the line. We are living on the edge of a phantom divide, and we don't know if we are on the gentle side or the one that leads to the rip. And all of this wondering, it keeps bringing us back to that one nagging quiet question, the one we can't seem to escape. The coincidence problem. Why now? Why are we here, in this one special fleeting cosmic moment, when the pull of dark matter 25% and the push of dark energy 70% are even in the same ballpark? In our standard story, these two things, the dark matter and the dark energy, are complete strangers. They are two separate, invisible, mysterious components. They don't talk, they don't interact, they have nothing to do with each other. And the fact that we are here right now to see them in this brief cosmic handover is just a coincidence. A random, lucky, meaningless Or is it? What if it's not a coincidence at all? What if they aren't strangers? What if the dark sector, that entire invisible 95% of the universe, is not two separate things but one interconnected ecosystem? This idea is called coupled dark energy or coupled quintessence. What if they are talking to each other? What if dark matter is slowly, steadily decaying into dark energy? Or what if that rolling quintessence field is leaking its energy into dark matter? What if there is a hidden connection? A flow of energy between the two, governed by a deeper law. If that were true, it would change everything. It would mean it's not a coincidence. It would mean that this balance we see is required. It would mean that the two components track each other, that as one fades, the other must by a law of nature grow. It would solve the coincidence problem. Not with luck, but with physics. With a deeper elegance. A universe where the two greatest mysteries are not two, but one. Is our rulebook wrong? Is the energy a phantom? Or are the two great dark invisible forces just two sides of the same single unknown coin? These are the questions from the edge. The whispers we hear when we stare into the 95% of the cosmos that we do not understand, And so after all these questions, after all these theories, these grand ideas, we come back to a silence. We are faced with the most unsettling and the most humbling fact of all. We cannot detect it. All of this 70% of the universe, this dominant shaping force, is invisible. Not just invisible like dark matter, which at least clumps together and pulls on things with its gravity, leaving a fingerprint we can trace. No, dark energy is profoundly invisible. It doesn't clump, it doesn't gather, it doesn't interact with light, it doesn't seem to interact with matter, it doesn't radiate anything, it doesn't absorb anything, it doesn't leave any tracks in our particle colliders, it doesn't leave any trace in our most sensitive detectors deep underground. We have built a science on the idea of testing, of touching, of isolating a thing and measuring it and poking it to see how it behaves. But you cannot poke the void. You cannot put empty space in a bottle, and take it to a lab and measure the energy inside. We have only inferred it. We know it exists, in the same way that you know the wind exists, not by seeing the wind, but by seeing the leaves on a distant tree begin to dance. We see the leaves of the cosmos, the galaxies, and we see them dancing. We see them accelerating away from us. And so we know something must be blowing, but we cannot feel the breeze on our skin. We are, in a way, stuck. We are stuck between a model that works perfectly, a story of the cosmos that fits every observation from the first light to the modern sky, and the uncomfortable somnolence of not knowing what the main character is. It leaves us in a kind of philosophical void. What does it mean to live in a universe where 95% of what is real is, and perhaps always will be, beyond our grasp? What does it mean when you look up at the night sky, at that brilliant, beautiful 5% slice of reality, and realize that it is the exception? We are the exception, the atoms that make us, the stars that shine. We are the anomaly. We are the trace ingredient, the tiny complex flecks of dust, floating in an ocean of something else entirely. For all our science, for all our progress, we are forced to admit that we are still at the very beginning. We are staring into an abyss of not knowing. And perhaps that is the real lesson. Perhaps the universe is not just a puzzle to be solved. Perhaps it is not just a mechanism to be understood. Perhaps it is a song. We are listeners, waking up in the middle of the night to a deep, beautiful and complex piece of music. We can hear the melody. We can hear it clearly. It's the expansion of space. We can map its notes. We can measure its tempo and how that tempo is accelerating. We can describe it. We can predict what the next note will be. We know the melody is real, but we do not know what instrument is playing it. It's an instrument we have never seen, an instrument we have no name for. We cannot imagine how it is built or who or what is playing it. And yet we know this strange, silent, invisible instrument is the only thing holding the music together. We know that without it, there would be no song. There would only be a silence. And so we just listen. We lie back and we look up into the darkness, and we listen to the grand, silent, beautiful music of the cosmos, a music that is all around us, a music that is us, and we just wonder.